but it's not a big deal.
Thank you. Maybe just make sure that if it asks you for permission, you give it. So if it says that,
should be fine. Should be fine.
Okay. So hello everyone. Welcome to the new iCog talk after a brief break. Our speaker today is Fulvio Mastrogiovanni. He is an associate professor at the University of Genova and currently also vice rector for international affairs. So his degrees, both the laurea and the PhD, are from the University of Genova. And he has also been a visiting professor at institutions in America, Europe, and Asia. More notably, he is a member also of the board of the PhD school in bioengineering and robotics, which was also my PhD school at India. And he has organized a lot of international scientific events, which include some of the big conferences that we all know, like Roman, IROS, ERF. And currently, so he teaches a lot of courses, among which robot architectures, human-robot interaction, and artificial intelligence for robotics. And he's also the founder of two spin-off companies from Unija, which is Teseo and IOSR. Sorry for mispronouncing.
No problem.
No. And okay, I mean, with that, I will like to welcome you and to invite you to give your talk on the natural and the artificial in artificial intelligence and cognitive architectures. Thank you very much.
So thank you, Anna, and thank you for being here. Actually, I teach too many courses. In fact. So what I really would like to share with you is some thoughts about some ideas that came into my mind lately. It's not a showcase of what we are doing in the group. It's just a sort of a discussion about some lessons learned that I mean a few lessons that I had the possibility to learn while trying to integrate AI components in software architectures for robots. So, and the idea, I started to do this quite quickly. I mean, personally, I'm a logician, and then a logician who tried to become a roboticist, and then still the theory is always in the background. Let's try to understand all together what in principle. So it's a sort of a discussion. And starting with the discussion, I try to put down a number of things that I personally believe a cognitive architecture should exhibit. I mean, it's not something particularly fundamental or insightful, but of course, a robot being able to understand from a cognitive standpoint the environment should be able to react to it, get knowledge from it, reasoning. I personally believe a lot in hierarchical and recursive forms of reasoning for some reasons. Learning from experience, of course, and of course, very important, memory, being able to interact, and lately being also able to show some emotions, and this trigger a number of interesting things. So let me pose initially the idea that eventually will be a sort of the conclusion of this 55 minutes that we will be together. So it is that, in my opinion, up to now, even considering past cognitive architectures, besides some very insightful ideas, the most focused activities right now is on engineering. So they're rather focusing on the engineering side, whereas I anticipate that, in my view, we should consider cognitive architectures as scientific endeavor. So, with falsifiability, hypothesis, and a continuous structuring of what the architecture should be. Also in terms of the kind of computational substrate that we are actually using. So I'm not going to cover all of this point. I will focus on very basic parts, on the first three. So I will talk about a bit of reactive execution, a bit of knowledge representation and inference, and slightly a bit of reasoning, using very basic formalisms and very basic ideas. And let's see that even in these cases, there are some things that are still, in my opinion, tricky. And we are probably tackling them from the wrong side. So key questions that we, starting now, we may ask to ourselves. So first of all, since cognitive architectures, when they have to be embodied, are to be translated in software up to now. So we should ask first if software engineering principles up to now are compatible with our ideas of robot cognition. First, maybe in the translation from the cognitive model to the software development, we are losing something. So we should ask this, in my opinion. Then when we want to include artificial intelligence techniques in a robot architecture that could exhibit some form of cognition, we should ask what are the assumptions in doing that and what are the limitations. Sometimes these assumptions are difficult to formalize. Sometimes they could be trivial, but hidden. And that's the bad part of the trade here. Then we should ask ourselves is if robot cognition could be considered a sort of a property of the algorithms that are implemented within specific modules of the architecture, or the morphology of the architecture could support inherently some cognitive capability. So it's something related to the technicalities, or is the structure of the architectures that makes it important. Beside the usual cognitive architectures, including memory, semantic, procedural, whatever. Of course, we have all of that. We want to have all of that. But when we put them down, again, in a software architecture, the question is whether we are losing something in that. And the last question, which in my opinion is the more complicated one, is what is, at the level of the architecture, the most natural description level for robot behaviors, and in particular for behaviors exhibiting some cognitive capability. So I will consider first the first three questions and later the last one. And of course, I will be very quick, but from the software perspective, the literature is quite clear about the software architecture for robotics. So we have hierarchical architectures. These are very classical. Reactive ones, behavior-based, not going to say anything new here, of course, plus something that's called hybrid reactive deliberative. That could be a good candidate for cognition. So if we want to summarize, the hierarchical could be slightly mapped to the old but gold sense reasoning or plan and act model. Much of the architectures are still based on that. So there is a sensing part, knowledge representation part, and then on the basis of the knowledge that we represent, some forms of action is there. So that's something that is still there. Reactive ones are in principle simpler. So we just remove the reasoning plan part, but of course they are interesting for other reasons that would be clear later. Behavior-based are quite complicated. The idea of behaviors or behavior-based architecture is that in the end you have many competing behaviors in principle, and you have one last synchronization point where either you put everything together on a competitive, on a cooperative basis. I mean, in the end, you have just one synthetic action by your robot. But behavior-based architectures are important because they are inherently multi-agent, if you want. But eventually, you have to condense everything in a specific action. Lastly, hybrid reactive deliberative are a good trade-off, are a good deal, because of course they try to combine sense plan act architectures with reactive ones. So the point is that reasoning and planning is not always there. So sometimes you have a direct connection between sense and act, and sometimes you recur to reasoning, depending on the semantics of the data that it's flowing. So this is just a state of the art from the 80s, not really a big deal right now. So in general, if we consider even recent papers, this is a scheme taken from a paper of mine that was published 6 months ago, even less, where we have the description of an architecture for human-robot collaboration. Well, we can say that currently state-of-the-art architecture that tries to include AI techniques, if you want, classical ones, are still based on this scheme. No, so you have a reddish layer on the left-hand side, perception and scene analysis. This is sense. It can have many forms, but it's a sensing part. Inside, you have this knowledge representation structure. There are many possibilities. I think probably the first iCog talk was by David Vernon, if I'm not mistaken. He described the CRUM architecture, where eventually he described with ontology, planning, etc. So it could be very similar. However, the knowledge representation structure then grounds a number of actions that the robot may perform and then goes to an execution, and that is the act part. In this case, we may think it's a sort of a hybrid reactive deliberative, in the sense that the planning part is an optional, in the sense that sometimes the architecture could plan, sometimes not, but everything from a software engineering point of view is encapsulated in the ontology. So the flow is from perception and scene analysis, data entering the ontology. The ontology may activate the planning. Planning could be back with a sequence of actions. These actions are represented within the ontology and then are executed via the execution module. So that's the idea. If planning is not necessary, we have a possibly reactive framework from scene analysis to execution. So we didn't progress so much. So let me now show a video. It should start, which is again part of our work done. I don't know if he's present here, with Kurosh Darwish, who is now a postdoc at IIT. I think he's working with Daniele Pucci. The idea here is to perform some collaborative experiment in human-robot collaboration for performing sort of joint assembly task. So what's the idea? The architecture is the same as I showed in the previous slide. I will explode it a little bit. So the robot is actually looking at the scene via a Kinect. So it has a point cloud, is able to segment the table, the objects they are in, it recognizes them. So it has all of this scene perception and whatever. And then we have sort of a collaborative structure whereby the robot and the human, who is now doing nothing, could collaborate, doing some turn taking in order to perform this sort of IKEA-like assembly table. So we have four videos here. In the first one, in the same collaborative model, the robot is doing everything alone. So it has a sort of a sequence of actions that could be either planned or scripted, not really relevant in this case. So the robot, as you see, is doing everything alone. In the end, the human is just fixing a little bit the legs to the table. If we move on a little bit, let me progress a little bit. The same architecture and the same collaborative model could be used to perform some turn taking. So the robot starts exactly as in the previous scenario. So it started to do things, but at the end, you can see that the action from the human is actually detected and the robot is able to react, not performing the actions according to the scripted plan. So, and then tries to move again, but the human again intervenes and in a sort of anticipating what the robot is actually doing. So it's sort of a planning in between context assessment for the robot actions, understanding what the human action, what the human is actually doing, and eventually anticipating or compensating for the human actions, doing something else. No, so in order to do that, there is a continuous planning. The robot is continuously understanding whether the plan is still valid and trying to compensating what the human is actually doing. You see, if the human is not intervening, the robot tries to follow the plan. Of course, when designing a software architecture like this, let me go, and all the possible combinations. Let me go at the end of the video where you see, let me say, like this, the four executions, so robot only and various combinations of robot plus humans. Of course, the software engineer tries to divide the sensing part from the knowledge representation part from the action part, and then you can realize, for instance, that in the fourth video, the objects that are actually assembled are slightly different. So in the top left, we have big tabletop plus long leg. Bottom left, big tabletop, small legs. So and the opposite. So top right, small. So, but the point is that good part of the architecture is independent from the perception part. So that's a good deal about sense plan act architecture. So as long as the interfaces are different, you don't consider them. So here you can see an explosion of this architecture in the sense that you have a clear sensing part, clear knowledge representation part, and a clear execution part. So again, we can, if we had a ROS-like structure or even a YARP-like structure or whatever kind of framework we would like to use, you have that these are modules, and eventually you encode specific behaviors, or that could be based on machine learning, planning, classical AI, whatever, inside a specific module. So that's the state of the art. But what is tricky in sense plan act architecture are, of course, the interfaces. And in particular are the interfaces between the sense layer and the reasoning layer, and the reasoning layer and the act layer. So that is everything. So the decision, the engineer that is actually modeling or describing an architecture should understand what are the metrics, and I will focus a little bit on those. Since I really would like also to focus on what it takes to encode AI techniques, planning techniques, for instance, inside an architecture like this, I really would like to tell you what are the kind of question that the AI guy is asking to him or herself when having to understand which kind of techniques I would like to use. And you can see that these kind of questions are the ones there on the right hand side are everything but cognitive. There is no cognition involved. So typically the kind of questions we ask ourselves are, can I use a non-complete algorithm? In the sense, a non-complete meaning it will find a solution. So maybe it will not find a solution even if a solution exists. So can I use it? Or how fast the algorithm can provide a solution to the rest of the architecture? Or how much memory it will use? Should I use a suboptimal algorithm if it uses less memory? Or do I need the best action sequence in that case? As you can see, these are very engineering-oriented questions. So nothing to do with the kind of techniques that we may have. On the other hand, someone more interested in the cognitive side of things should ask different kind of questions. So when encoding the AI technique, what can I know about the environment? So my sensing layer, what kind of information can provide to me? Do I have suitable feature extraction algorithms to support my reasoning? Can I specify the goals? I mean, in other terms, are the goals provided by the human, or can I support my own goal definition on the basis of the context? How does the internal representation, which is explicit most of the time in these cases, interact with the sense and act component? So these are the kind of questions that from a cognitive perspective, the one who wants to include AI techniques in a software architecture should ask. So going about reasoning, nowadays there are various techniques, but there is a sort of a consensus among the AI community about the use of certain tools, and in particular certain planning-based approaches that proved quite computational, well suited to describe current states, robot actions, goals, and plans. But all of them are based on a very logic-oriented formalism. So in these cases, for instance, one is asked to decide what are, for instance, the kind of types your reasoning should support. So you are defining your own object types, your own concepts in terms of types. You may define typed variables. You may define what are the constants in your environment. You define what are the predicative knowledge that your robot is actually using. So whether, for instance, an object is pushable, or what is the orientation of a certain piece of furniture on the table. But it's very logic-based. So you're defining, so if anybody of you have even used maybe just once PDDL, knows that you are defining the types. Of course, you have a grammar that you have to use, but in principle, you may define concepts that cannot be easily grounded to the kind of information that the robot can attain. So I can write down nice predicate indicating whether an object on the table is pushable, but I have to, first of all, being able to push it, and I have to be sure it is pushable. So by structuring, bootstrapping experience in principle, everything I write here in terms of predicate should be connected to what I can do in the real world. And this is a very old problem that is still there. I think the paper introducing the symbol grounding problem by Stephen Harnad has been published in 1990. So the idea of connecting the symbols in your system with the information that you can get from the environment is still the problem that any sense plan act architecture must actually follow. Well, as I said, planning, I mean, AI planning nowadays is just still a variant of strips. And in particular, nowadays, people are using variants, either deterministic or probabilistic, of this planning domain definition language, PDDL, which is this appendix of the big conceptual boom, which was strips. As you know, I like to think about it because strips was, as a matter of fact, was one of the cornerstones of the shaky robot. So in terms of, I can say, in terms of AI planning, apart a number of details which are of course, very important, but I couldn't say we, conceptually speaking, went far too much with respect to strips. So the basic principles are still there. Of course, now we have probabilistic planning. Computationally speaking, they are quite good. They use internal heuristics, but still, the conceptual tools are still there. No, but let's dwell a little bit on a very simple description of actions in strips, and let's see what are the tricks. So for those of you who investigated a bit of strips, you know that the first thing coming on the page is the blocks word. So you want your robot to actually manipulate blocks, stack them, unstack them, and putting them on the table. No, yeah. So I really would say that is a scenario that is still there. No, so when you see robots having to manipulate objects in clutter, so it's still a blocks word problem. So we still use blocks, we still use colors, or we still use objects of a given shape. So most of the time. So in terms of an action, so what is a typical strips stack action? You have a robot who must stack one block B1 on top of another B2 blocks. Question mark are B1 and B2 are variables. Robot block are types. In order to perform this action, you need a precondition list. So what are the fragments of the environment that must hold true for the action to be executable, or I would say, plannable, okay, although it's not the proper word. So in order to stack block B1 on block B2, we assume that block B1 should be on the table. Block B1 doesn't have anything on top of it, and B2 doesn't have anything on top of it. So these are our preconditions. The predicates on table, clear top, are invented by us. So we assume that conceptually speaking, the stack action could be triggered whether in the word those truths are valid. Once the action is executed, we say that becomes true another predicate, which is on B1, B2. So block B1 is on block B2. So with that, we give this semantics to that. And after the action has been executed, B1 is not on table anymore because we picked it and we put it on top of block B2. And B2 is not anymore clear. So it has something on top of it. So strips planning goes on by adding and removing predicates from the symbolic state, which is the list of predicates holding right now, on the basis of the actions that we carried out. So we should specify all of these actions in terms of preconditions, add list and delete list on the basis of predicates that we think are a good description level for the reality we want to model. And this is, for instance, what could happen. So we say that we have one robot and two blocks that we called A and B. So the star state left-hand side is that the block A, the blue one, is on the table. It doesn't have anything on top of it. B is another block, is the red one. It doesn't have anything on top of it. And we specify a goal state. We want that A at the end of the planning process be located on B, which is the situation on the right-hand side. This is, of course, is a very simple example in the sense that in order to do that, we just need to perform one action, which is stack. So if you consider the star state is compatible with the precondition list of our stack action, you can see on table, clear top, and the precondition list is on table B1, clear top, clear top. So it is just a stupid example. So the plan is just stack. So the robot should stack the block A on top of block B, and that's the planning process. So the planning process in this case, just one action, could be very complicated. Actually, there are these big competitions where the system should plan beforehand hundreds and hundreds of actions. One may ask, what's the point of planning so many actions in advance? But it is just for the competitions. But in general, once you plan, as they say, at least you have a plan. So the sequence of actions that you now have can be submitted to our execution layer. And then the point is trying to understand what does it take to pass from a symbolic representation of the stack action to the real execution of a motion implementing a stack action. And that's the big deal. So I will be back on this in a few moments. So let's focus on the tricky part between the sense and the reasoning planning layer. So again, let's consider our stack action and the plan that we just devised. But let's do one thing. Let's consider first the stack action, we say in logic terms, grounded. Okay, so I substitute in place of question mark R, question mark B1, and question mark B2, which were my variables, the constants associated to the blocks. No, so and I have the stack action. So I have that A is on table, clear top A, and clear top B. So if I want to execute the stack action, I must be sure at runtime that on table, clear top A and clear top B are valid. Okay, so of course, in the planning phase, you plan something. In the execution phase, you must be sure that the precondition using which you planned are still valid. Why? Because maybe the word has changed, or maybe there is a human the robot is interacting with that who, in the meantime, has picked up block A and put it down in another container, for instance. So the word has changed. So planning, as I said, is just a plan, but you must continuously question it while you are running, while the robot is actually moving. So the point is that we are writing predicates like on table, clear top, or on, whatever, but these predicates, truth values, will have to be monitored at runtime. So you need to have a sense architecture, a sense module that actually tells you whether an object is on the table. So every time we, as an AI designer, we think about a predicate, and in this case is on table, we are assuming that is either available or to be implemented a sensing algorithm that will actually tell me eventually whether that predicate is true or not during execution. If not, I'm building an inconsistent architecture because I'm planning on the basis of some information which I cannot verify in the real world when I will actually execute it. This is a strong assumption that it's probably sometimes obvious, but imposes some constraint on the rest of the architecture. The same thing when for clear top. So with clear top, the semantics, the meaning is we assume the block A doesn't have anything on top of it. So this means that in our scene, in our point cloud, we need to segment the image, isolating A, understanding the geometrical, the spatial relationships between the objects in the image, and understanding whether there is an object located on top of A. So that's the hidden assumption when one writes down those predicates and is basing the whole planning phase on those predicates. So, of course, this is a very strong assumption, but it is also related not only to the precondition list, but also to the outcome of the execution of the action. So, for instance, if I want to be sure about the successful execution of the stack action, according to the plan, I know what I should expect. So I should expect that the block A will be located on top of B, and then A will no longer be on the table, at least. So I need proper algorithms telling me exactly that. So I need an algorithm telling me whether one object is on top of the other one, for instance. If that is what happens in a, let's say, in a full sensing cycle is validated, then I can keep on with the planning. Otherwise, I have to sort of replan. And that is exactly what's the trick of the architecture. So when we say here object and scene perception, I assume that the information that is actually provided to our knowledge base is in a form compatible with the predicates. Okay, it's something having a point cloud in input and generating symbols in output. Symbols could be either deterministic or probabilistic, which is probably something that we are actually doing. But of course, if they are probabilistic, this will imply certain use of the knowledge representation structures that I can use. So if my knowledge about the environment is probabilistic, of course, I cannot use a deterministic knowledge representation layer. It should be probabilistic if I want to fully exploit its information. And that's why, of course, all of us are going into full pre-processing, whatever. And then what we should read, semantically speaking, when we see point clouds, for instance, associated to our human-robot collaboration scenario, where the robot is not just segmenting the point cloud, but is deriving predicates telling that the specific leg of the table is fixed to the tabletop. So the leg in that case is on top of the tabletop. So we have a predicate making that explicit in the system. Of course, this is just for purpose. One may even use this kind of techniques to try to learn what are the spatial relationships among the objects in a scene and trying to derive a sort of a graph of the various scenes. So we have been doing work in the past exploiting these logic-based spatial relationships, whereby by showing a robot via, in a static way, a camera, this sequence of 10 scenes, we can, for instance, understanding what are the spatial relationships and the relationships among the scenes. And we may ask the robot, like, you are in scene number epsilon 21, what actions are needed to generate a scene epsilon 53? So, and the robot understand what are the differences between the scenes in a logic way, depending on the missing predicates, and try to plan accordingly. So once you go to the logic symbolic layer, of course, you have the full-fledged possibility of planning. So you go to the other side, and once we plan an action stack, robot A and B, of course, we have quite big of a problem when we want to execute it. First of all, where are A and B? What are A and B? So we have a symbol A that is related to a portion of the point cloud, but also probably stack is not an atomic action. The robot will have to perform maybe reaching A, grasping A, reaching B, releasing A on top of V. So there are the grasping points associated with that, motion planning, inverse kinematics. But the point is that the hidden thing that we did in the blocks world, and we did it mostly for granted, it was that stack was the proper level of description in the blocks world. But stack is everything but an atomic action. So the point is, should I use stack or should I model reaching, grasping, releasing inside PDDL? Because if I model stack, I have an atomic action that most of the time corresponds to a sort of a scripted execution. No? So stack is, I mean, almost always reaching one point, grasping something, reaching another point, and releasing something on top of the previous object. But of course, on the other hand, if I want to be more flexible, I can try to substitute stack with reaching, grasping, releasing, but then I have more action in the library of the planning possibilities, and that, of course, corresponds to an increased computational burden on the planner. So the more actions, the more predicates, exponentially leads to a problem in the computational load of the planner. So that's one thing. So in the planning domain, you always try to define a trade-off between the proper level of detail in terms of atomic actions and predicates, and how close you are to the to the real robot actions, the real atomic robot actions. And of course, we are assuming, as I said, that A and B are still in the same situation where we have found them while we were planning a few seconds ago. I'm not talking about milliseconds, could be seconds. But of course, we need to establish a geometric mapping about A, the point cloud corresponding to A, where A is, where B is, whether B is graspable, whether A is graspable. Maybe A, it's a small cube of uranium that it's too heavy to be grasped. What will happen to the plan? So if we do not model the physics, for instance, all of these are pure geometrical actions. So that's why an increasingly important track of research is related to formalism, dealing with combined integrated task motion planning, where while you are doing the planning at the high level, you're also integrating simulators in the loop, geometrical simulators that are integrated with up-to-date geometrical information to check whether certain actions are feasible. And that's why, for instance, in the architecture, now you can see there is a simulator here connected with the robot execution manager and the planner, which is, it's part of the knowledge base and part of the path planner here. So the robot execution manager all the time, while the robot is planning stack, unstack, release, all that action is associated to an in-the-loop geometrical simulator based on the currently up-to-date sensory information. And that's it's a bit the basic of task motion planning. Of course, while you progressed with the plan execution, certain things could be still compatible with the preconditions that started the planning. Others may not be valid anymore. So this is, for instance, another video done with other colleagues, where we ask a robot to manipulate on the table an articulated object. Here, perception is simplified by the presence of a number of QR codes. So the idea is that the robot has an internal representation of the geometrical configuration of the articulated objects. So for instance, it has that shape, and we provide it with a sort of a goal configuration for the object. So the robot here execute action by action, okay, moving very dangerously to the table, thanks to the camera calibration. That doesn't happen, but and then it performs a sequence of actions, just rotating the object. So the idea is to obtain a certain configuration. But as you can see, the human is continuously, slightly modifying the object configuration or the positions, or slightly moving the QR code. So at every time instant, okay, this is not really a sexy interface, but in a while should arrive something better. So here you have the typical interface where you have the predicates on the left-hand side. I can pause just 1 second. As you can see, I don't know if you can see, but here you have a number of predicates. For instance, has angle, link. So you can say that certain link is associated with a certain angle. These are the mission goals, and then you have the facts on here on the which is affected. So how the links are structured, how moving one link affect the configuration of the other links. Okay, so this is, I mean, everything is managed within the system. So we can define plans, checking what are the target angles that we want to implement, and then once we do it, what are the mission goals, we can add and remove predicates. Of course, I mean, a cognitive agent should be able to elaborate its own goals in terms of the predicates that are needed to attain that goal. And you can see here a gazebo-like simulator, and this is the in-the-loop simulator. Okay, so and you can see there is a slightly different, because here we have mapped what the robot was planning at the beginning. I mean, during the execution of the planner, and what we are actually doing at runtime. No, so it is like in a cognitive inspired way. It is like when you are thinking how you will actually do a certain action. So you are planning a certain action, but you visualize you moving in the environment, picking up that objects, crossing that door before actually doing it. So with the simulator in the loop, we are trying to mimicking a bit with this task motion planning thing, how the robot may behave in the future. In fact, there is a line of research that we are trying to push, which is not really, I mean, we are not the first, providing the robot with the capability of autonomously perform its own simulation. So building autonomously synthetic goals in simulation in order to build a look-ahead plan to be executed later, or to use them as a sort of a library of pre-available plans. And this is one thing. These kind of models could also be integrated with naive physics. And this is quite relevant because although in the previous video I showed that the articulated object was on the table, one may think about how to integrate gravity, for instance. So the simulator can even be used to integrate how, for instance, the physics of the word could be relevant in this case. And finally, there is the act part, and this is the realm of what I call task motion planning, where eventually we have to consider that in action planning, you actually plan for actions without considering whether those actions could be executed by the real robot. So having the in-the-loop simulator helps doing that. There are a number of approaches based on task motion planning, has been formulated by Lozano Perez many years ago, not really relevant in this case. But the point is that almost all approaches are based on a notion whereby while you are planning, you must plan not the sequence of actions first and then you execute them, but to provide an integrated task motion planner. So the outcome of the plan will be not just the sequence of actions, but the sequence of motions. In order to tell you an alternative view about how this kind of things could be used, we have integrated the whole architecture and task motion planning. So with this simulation in the loop, with a augmented reality interface for human users, and you will see here an example whereby one of our students is actually interacting with the robot. But you will see that the interaction is quite peculiar in the sense that, now let me stop at the proper, no, sorry. Probably let's go back if you, okay. As you can see, I don't know if you can see from the Zoom connection, but there is a simulated model of the Baxter actually superimposed with the real Baxter, okay? Probably you cannot see it, it will be clear later. So with the HoloLens, so here on the left-hand side, we are perceiving the HoloLens view. We have superimposed the simulator, the view of the simulator with respect to the real view, okay? So we have this augmented reality thing whereby we have this gazebo grounded simulator of the Baxter actually superimposed with the real Baxter on the HoloLens camera view.
It's visible a bit in the grippers.
Yes, yes, but now it will be more clear. Always these nice interfaces. I mean, I started, as many here, developing code when ROS or YARP were not even available. So I like low-level interfaces. Okay, so as you can see here, probably, there is this graphical model here, which is the future position, the future pose of the arm, as determined by the simulator, and it's visible for the human. Then, of course, the robot at best, of course, you have also to consider that the superposition between the real Baxter and the 3D reconstruction is not perfect, okay? There are some small calibration things. Of course, we can use the augmented reality thing also to include, as many are doing, augmented information about the workspace, whatever. But the simulator in the loop can serve, you can see now the superposition was not present. So, but the in the loop simulator can be used for different purposes. First, to perform this architecture specific task motion planning thing. So the robot, before planning an action, a pickup action, as you can see, different from the simulator, it can check for its feasibility, but it can also provide this information to a human user. And in fact, this study is not related to task motion planning. It is a sort of a byproduct, but you're using it to check whether this kind of interface could improve the sort of interaction or collaboration that we have with the human. So whether the knowledge of what the robot will do in the next few seconds in a sort of a hopefully intuitive way could lead to a better acceptance of this kind of technology here. Okay. So going to the very last part, on the basis of this, I would like now to pose a number of hypotheses, because what we have been seeing is that in the current architecture based on AI, whatever, there are numbers, symbols, there are constraints, predicates, modules are separated. From the software engineering perspective, you have modules, interfaces, messages going on. It's very engineering-like, okay? So not really cognitive, in my opinion. So my hypothesis is that, in my opinion, the robot software architecture should be made a bit more abstract and should be considered as a sort of computational theory, a real computational theory. Developing a software architecture is to develop a theory of something that we should understand what should be, but should ground modeling cognitive behaviors. Cognitive behaviors, in my view, should emerge as the coordinated activity of different modules, which seems obvious, but as you can see, not a single part of the architecture has it all. So you have symbols in a certain part, actions on other parts. The symbols in the knowledge representation layer implies entire software modules. So you cannot consider them as isolated part. Such a computational theory should support the representation and use of both continuous and discrete information, so numerical, symbolic. Why? Because as an engineer, symbols for me are surrogate of something that should emerge from numbers. But since I'm not able to make it emerge, I define the symbol explicitly. So at the best of a scientific effort, symbols are to be considered, in my view, as placeholders. That should be replaced in the end. Maybe. In fact, any engineered symbol should correspond to appropriate numerical or perceived phenomenological information, either related to the sensing part, which is the old symbol grounding problem, or related to the motion part, which is related to a real motion problem. In the end, robots move in a sense in 3D space. So from the symbol space to the 3D space, something should happen. And then I leave the last 5 minutes to question number 4, whether is there an appropriate computational theory now for cognitive behaviors for robot. I mean, I would like to question whether engineered software architecture based on numbers and symbols and knowledge representations and predicates are an appropriate level of description. And that's the point. So, and that's what we are actually doing. These kind of questions remind me of a similar, definitely more important question that was asked a lot of years ago in a very famous paper, which is, can quantum mechanical description of physical reality be considered complete? But if one looks at the specific questions that are done in the text, we should ask ourselves, in my opinion, whether our architectures as a computational theory is correct, whether the kind of behaviors that can be generated from these architectures are appropriate. I'm not talking about completeness. I'm not able to do that. And we should also consider whether we really want that every element, every symbol, every bit of information that is represented within the architecture should correspond either to something that is sensed or should lead to something that should act. So in my opinion, the problem of the interface between how we represent knowledge and how we get knowledge in and how we exploit that knowledge is central in this case. And I want to conclude with this 5 minutes about an architecture that we are building. It's sort of an experiment that we are doing together with some other colleagues, definitely more expert than mine on this thing. So we have been lucky to do this, to carry out this cooperation with the Tokyo-based IBM quantum computing center, and having access to a number of quantum computers from IBM, and we're working together with our colleagues in physics, working on quantum computing. We are trying to devise architectures for robot that, of course, now are based on the very old von Neumann model, but eventually are thought to work on the new computational theory leveraged by quantum computer by starting from the beginning. So by taking again Breitenberg's vehicles and re-implementing them and see in a quantum inspired framework. So of course, this we have published a few papers now on that. Just as sort of a proposal. No? So first of all, why quantum computing is appealing for me? Maybe I'm the only one in this respect. So first of all, seems like we can, instead of having heterogeneity in how we represent information, symbols, numbers, we can have a sort of a unit of information good for representing knowledge at different levels of detail. And instead of having separated software modules with the interfaces that are a bit arbitrary, we have just these atomic units, and this is something that, in my opinion, is quite good. There are a number of properties from quantum computing that are appealing to us, especially for perception. In fact, in the past few years, there has been a lot of work in quantum psychology, especially, which takes inspiration from some computational perspective, especially in perception, in visual perception. I mean, again, I'm not an expert in that, but appealing the kind of computational mathematical modeling that you can do about that. For me, what is appealing is one specific point, which is related more to the human semantic space modeling and semantic analysis. So how we can associate certain I wouldn't say symbolic information, but something that could be as expressive as symbolic information in terms of quantum theory. We started from some quantum formalism from binocular rivalry that was quite inspiring from us, being able to move in between different percepts when they are ambiguous, and there are nice models for that. But the idea that we have right now is not just to use the tools of quantum computing, but to organize a quantum robot architecture. Okay, so where we do not isolate the quantum computing algorithm inside a module, but everything should be done using this formalism here. So basically, simply speaking, you can imagine it as really a sort of a behavior-based architecture where you have input qubits, output qubits associated to sensors, and internally an architectures where different qubits are put together. So the output of one qubit is an input of another one. I'm not going to cover quantum computing here, but I would like just to show you what a quantum inspired architecture looks like. So for doing that, as I said, we were inspired by the Breitenberg's vehicles, but I like to show these figures. I mean, this picture here that should be quite known, taken from the subsumption architecture from Rodney, because the idea is to start from the beginning. So our first robots based on quantum computation should avoid objects and then wander and then explore, etc., etc. So that's the idea. So starting from the beginning, it's like being again a sort of a small pioneer. So we like a lot Breitenberg vehicles, and on the basis of the architecture that we call the Q-brain, we have a number of sensor interfaces, which are just numerical, just one vector numerical interfaces, actuator interfaces, and then you can imagine that in principle, or you have an n layer structures of qubits, like a big neural network where each neuron is indeed, has a certain configuration, has a certain functioning. We started with one first paper, which was a preliminary study about quantum perceptions for robot. This is available on arXiv, and soon being published also. We performed a second one where we actually fused, we perform multisensory integration using cameras. So we basically replicated binocular rivalry by showing robots certain configurations of objects that were not quite clear. And we started implementing, as I said, Breitenberg vehicles. So the first is the vehicle number 1, according to the Breitenberg classification. It's on the bottom right. I put a small Breitenberg-like one. So the one that actually goes close to the source of light, to the light source. And you can see this is, okay, again, I don't want to go to the details, but and you can see it's quite in principle easy. We have 2 qubits, one dealing with what happens with the left light sensor, one with what happens with the right light sensor, each one attached to an actuator, in a sense. Okay, of course, are numbers in the end, but the point is that talking about the computational theory, these are just numbers. Okay, so like in all behavior-based architectures, could this be another substrates? So could this be something that allow us not to use symbols? Because if I have to re-implement the Breitenberg vehicle number 1 using ROS, of course, I have a completely different architecture where certain information should be made explicit. I should process the data. I should have processes running at the same time, or a logic formalism saying to me, go to the left or go to the right, or having a vector. So in ROS terms, the substrate could be definitely more complicated. The most advanced robots that we have right now, it's a bug-like robot. So I worked in the past in bug-like algorithms. So I'm particularly happy to be able to do really that, but it's not that bug-like. So it has 2 cameras, left camera, right camera. It has also a presence sensor. It has a subsumption-like Q-brain, where you have all these connections, and it can exhibit, let's say, 5 behaviors. So rotate right, rotate left, move backward, move forwards, and bite because there are some other bugs around. So we have this multi-bug scenario. So again, I'm not showing the video here. There are the videos on the links of the paper that I showed, and you will not notice any difference with respect to the typical gazebo simulators that you can find when there is ROS hidden. So what could be a possible approach that I personally would like to pursue in the future? So in my opinion, we should use current state-of-the-art software engineering approaches intended as the computational theory as a theory. So up to the moment, we need them. If there is a better description available, that could be whatever. So in terms of if we can remove symbols and making a symbol emerge from numbers, that could be one possibility. So we go back and we, like quantum theory actually was replacing classical mechanics in certain parts, we should actually substitute that theory. So software architecture shouldn't be considered as sculpted in stone, but should something that we reevaluate always. Of course, so just to summarize, what is natural and artificial? We tend to think when we introduce AI, I mean, AI itself is artificial intelligence as something opposed to biology. No? Artificial is kind of intelligence that is different from the biological intelligence. But I think in this case, what is artificial is the old theory, and we progressively should move towards the new natural one, which will become artificial when a new natural, more basic architecture or computational theory will be there. So this is done by many people, not by me, and I'm not doing anything anymore. And this the end of my talk, maybe not the end. So thank you, and sorry for being a bit long.
Thank you very much, Fulvio.
Thanks.
Stop sharing.
Thank you.
Okay. So, as you know the drill, so if you want to ask questions, you can feel free to unmute yourself and also turn on the camera so we can see you. Or if we have more people, we can use also a Q and raise hand option, or write them in the chat. But I encourage you to ask so we have a bit of interaction. I'm giving people some space before I start bombarding.
Okay. Well, maybe I can start. Just we want to break the. So I mean, at the end, what you are proposing is to change computational models. I mean, to use this, quantum approach, which I don't know personally very well. So I will not even attempt to try to ask questions about that. But what somehow surprised, not surprised, but I mean, the kind of question I would like to ask is, we started many years ago with Breitenberg's vehicles, and we try to have some more, cognitive abilities, trying to implement whatever we can, etc., and so on and so forth. And now you are proposing to go back to Valentino Breitenberg's vehicle, which is perfectly okay. I'm not saying anything. I mean, if you want to try a new path, you have to start from the beginning. So that's for sure. But you should at least have some hints, even if not explicit, some hints about the fact that this may be a better way to go, this new approach. So I'm just it's not a scientific question. It's just your gut feeling about this. What is the reason why you think this is maybe a different solution?
Well, my gut feeling is this. I mean, what I started to realize. I mean, at least it's a feeling, no?
Yes.
Is that maybe we may suffer a bit of tunnel vision. So what we do is engineering, no? So software architectures, we copy paste code, we have all these things, whatever. But engineering is by definition confined in what is known to be possible. No, so in principle, you say this is the perimeter, and I will move inside. no? So, and that's why you put together different techniques. I mean, I didn't talk about machine learning, for instance, but AI symbols, and we confine all of this structure into small modules, and we have artificial interfaces or artificious interfaces. And then the end is that you have, in the end, messages running inside your system that are time-stamped. You need to fuse information that is not up to date. The robots are quite slow, no, because real time, I mean, part of it is real time, part not. So my point is that that is good, and we can go on. We can keep doing the very last bit of engineering, like the Tour Eiffel of the mechanics. Like the great thing, but eventually the perimeter is already set, unless there is. We try to think about questioning whether that is the framework. So I'm not really proposing quantum computing, because I'm really proposing anything that is questioning this paradigm, even contrary to my own interest. I mean, scientific one, in the sense that doing teaching, software, architecture, AI, whatever, that's perfectly fine. So I could keep going on for the next 30 years, doing the same thing, specializing modules by modules, but questioning whether that is the option.
Yeah.
I mean, whether that will lead to cognition.
Yes, yes, yes.
And that's the gut feeling.
Okay. Thanks. I have other questions, but I don't want to steal if there are other. Yeah. With this.
Yeah. I just like to comment, and also I have a question. First of all, thanks for the great talk, and also what you just said in response to Giulio. It was also really nice that you pointed out and very clearly showed that a lot of architectures that were developed in the 1980s, so you know, a lot of basic ideas are actually still dominating what we have today, of course, in a more sophisticated way, and you know, with many more modifications, improvements, and so on. But so I do actually, although I know nothing about quantum computers, but I do sympathize with your feeling that maybe there has to be something else. But going back to my question, in your experiment about the human-robot interaction, you had the simulation. And I noticed that the simulation, although you said several times it's with updated sensory information because it needs to be updated, but I noticed it was not directly connected actually to the sensing part. It went via the ontology, so the more planning and knowledge representation side. I just wonder, was that a deliberate decision? Because I was thinking in your videos, the objects were static. Well, sometimes the human moved them a bit, but they were not moving themselves, or there was no really quick movement. So could you maybe reflect a little bit more on the simulation and how it could deal with very dynamic environments?
Yes. Well, indeed, that's, in my opinion, one key central point in the limitations of this kind of architecture. So when you have, I mean, that was in the example of sense, plan, act. If you consider it, the act part is not directly connected to the sense part. I mean, formally speaking, no? Then of course one can do whatever, no? But in general, the only information that the simulator has about the current status of the environment is in the central knowledge representation layer, no? So it's still reading information from that. So is the sensing part providing information to the knowledge representation layer, and the knowledge representation layer providing information to the simulator upon request, in a sense. So this is the only connection. But of course, this is exactly my point. I mean, one of my point is, of course, that architecture is quite standard. I mean, when I say standard, I mean that having to teach software architectures for robots every year, I update a very long report that I have about all the architectures. I mean, last papers, whatever, and they're always the same. Apart from a few notable exceptions, of course. I'm not saying, but the majority of them still employ this kind of concepts, no separation or segregation, if you want, among the various techniques involved. That is central. No, in fact, the kind of I think there is a divide between those trying to build or to engineer, let me say this, a fully fledged sensory motor architectures where you have a real loop, I mean, a continuous loop, and the real engineering need to write software. In the end, there is something that starts to be set up apart. And that's one example is the simulator that you were mentioning. That is, I mean, why we need a simulator when we have the word directly in front of us?
Yeah.
Okay, so and that's the, but this is not, I'm not the first to ask this question, right? So I think it has been asked in 86 or 87, if I'm not.
Yeah, Watney Books coined some very nice phrases. Yeah.
In fact, no, but still,
I like to quote him a lot. So.
But still, there is this new task motion planning approach. There are many papers now in task motion planning. Still assume that the planner essentially make use of a simulator to ground possible future outcome of actions. But still a simulator is not a real word.
Absolutely. Yeah, which is really worrying, because these days, you know, a lot of people talk about robots that will operate in very dynamic environments, in hospitals, in care homes. And, you know, these are really, really difficult environments. Lots of things move around and are unpredictable. And so, yeah. Okay. Yeah. Thank you.
Well, you're welcome, Kirsten.
Lorenzo, we don't hear you very well if you're trying to speak.
Yeah. Yeah, probably. I don't know. You don't seem muted. I don't know.
No, I think he's using maybe like Bluetooth, but the microphone is not. No, Lorenzo, we still don't hear you. Maybe you can try to change the audio settings or to rejoin with a different audio. Or also in the meantime, you can write the question in the chat.
Can you hear me now?
Yes.
Yeah, sorry, I don't use it every day. The Zoom is sometimes the default are not correct. So yeah, my question was about the way you presented some ways to describe the knowledge of the robot and also to plan an action. And I was wondering if you have some ideas or how to describe behaviors and the environment in a way that you can reason about, because I noticed that then later you switch to using simulations, which is a good way to sort of anticipate the future, but I don't, at least to me, it's not obvious to understand how you can use that to reason in the way you were doing when you were showing the stacking.
Yes. Of course, I mean, this is a very good, I mean, questions. I think it's at the center, it's sort of a cornerstone of this kind of architecture here and their limitations. So first of all, I have, I mean, shown this. To be completely honest, the knowledge representation layer used in that case, I mean, the one that I show is quite basic. There are many formalism, but you know better than me, to ground in this kind of formalism uncertainties or whatever. So assuming that we use those kind of formalisms, So, for instance, now we are exploring knowledge representation based on fuzzy logic. So using fuzzy ontologies in particular that are quite nice because you do not have the probabilistic interpretation, but you have the fuzzy interpretation that is, you can, I mean, you can associate not the outcome of a probability, but as a sort of fuzzy membership to certain concepts. Okay, so having the possibility of introducing certain a certain level of flexibility in the representation, what I believe is that the majority of the work many people are actually doing, me included, although I will come back to your question, is still based on a very old idea of how we represent things. So if we, well, now it's a bit of a joke, but if we read Kant, the description, the phenomenological description of the objects given by Kant could be mapped one-to-one to a knowledge representation system based on ontologies. So we represent objects based on a color, whatever, shape, if we have tactile features, that kind of tactile elements. So by enumeration, or of course, once, depending on the context and depending on the knowledge representation that you may use, you can have some form of representation tailored for the action. So for instance, I mean, affordances being one of the most known. What are we trying to do right now, which was not, to be honest, part of that experiment, is to describe objects on the basis of the relation. Oh, sorry, because so is to describe objects in a contextual way, on the basis of the scenes that the robot is actually looking at. So, for instance, if an object is engaged in a spatial relationship, we may prefer representing the scene that the robot is perceiving, not in terms of the objects they're in, but in terms of the spatial relationships that the objects are engaged into. Because what I really would like to is to be able to say that object is part of a given configuration, or has been used as part of a given past action, and for that reasons could be used in a certain way. So if you want, could be related to affordances, but I really wouldn't like to describe a hammer or a stone, but I would like to describe an object as something that can be used to hit a nail. For that, the object and, sorry, the stone and the hammer are the same, no? So it's very like to the notion of affordance, but still very difficult, in my opinion, to ground this information in a logic-based knowledge representation framework. Another thing that, in my opinion, is still very artificial is the symbol grounding, no? So the object may have the box. I have a box, it's called A, it's blue, whatever the weight, and let's assume I can know that. But then how can I connect it to the point cloud? I mean, I can of course associate a vector of information to that, but still, in my opinion, not very satisfying. So I should be able to determine the point cloud associated to that object on the fly, opportunistically, on the basis of the action I should carry out on that object. So I don't have a real answer, but a lot of doubts. So in my opinion, these are the things that are missing. So this kind of thing. So we are quite good in representing extensively knowledge, associating even to numbers in terms of positions of the associated point cloud, or a pose, a reference frame, whatever. That is, in my opinion, it's a sort of a commodity, no? So the point now is to question whether that is the way to go, or we keep it as it is, or we question it, as you were implying. No, probably.
Yeah, thank you. I had another, maybe this is just a comment. One thing that I think is important in describing architectures, and I see many times is neglected, is from a software engineering point of view, is the interfaces between the blocks. So you see blocks, functional blocks, there is a description of what they do, and then there are arrows that are not specifying what exactly these modules, these blocks are exchanging. And yeah, this is, I think it's a limitation. And sometimes it's not easy because these blocks are very generic, so they exchange information that is heterogeneous. But I think this is it's an important point. I don't know if you have.
Well, I can, yes, yeah. You are definitely right. I can tell you that when I teach, when I have this course, software architectures for robotics, I don't know why, because for me it's a natural concept, but I don't know why, and probably I'm not good enough to show this. One of the most complicated things, in my opinion, to teach is the dynamic aspects of the architecture, because we are primed with the UML scheme, as you said, even if we write everything in the arrows, no? And then I said, okay, look, but these modules, for instance, if they're implemented in ROS or in whatever, these are processes. And then you have a scheduler. So it's not really true that you have a flow of information going from process one to process two like it is, because it is the temporal dimension of what happens, which is conceptual, no, is could be completely overthrown by the scheduler. No, of course you have that on average things work. No, but this thing, so the dynamic aspects, the fact that you have an interface, the fact that you have a temporal diagram, then it's something that I don't know why, but I teach this course from 2011. Wasn't really able. I mean, I'm never sure they got it. No, never. So the temporal aspect is important. Sorry.
No, sorry for interrupting. No, but I was about to also add a comment on this. I think it also, because there you see the distinction between the software and the middleware, because all of the modules is the thing that it's most interoperable between different robots. At least for us, developing the actual module, the actual blocks are developed in software. They can very easily be ported on any different robot, whereas the flow of information, it's where it's really connected. Like you said, to ROS or to YARP, it's where the middleware of the robot comes into question. And depending on how people have been exposed, maybe it's not as easy to understand if it's something done in scheduling, if it's something done in publishing a topic.
Well, yeah, I mean, again, going back to the initial proposal, in my opinion, for this we are, I mean, at least I am so concerned about designing a software architecture that is flexible, modular, replicable, and reusable, blah blah blah. That is defining so many constraints about how we think about the architecture that could impose some hidden limitations. No, we are auto-imposing certain limitations in the name of flexibility, reusability. So, and that's why I say that sometimes software engineering is maybe leaving us a bit of tunnel vision.
No, yes. No. I mean, if I can intervene.
I mean, maybe.
Yeah, no. I fully agree with you. I mean, certainly. I mean, that's the reason why I think we need some kind of actions, joint actions. Because we may need to release some of the constraints that we are imposing on the software architecture to make it flexible, as you are saying, or more general, in order to implement the architecture based on cognitive abilities that we have in mind. But I mean, I agree with you about that. On the other hand, I think we need the kind of expertise which is needed from the software point of view to implement the kind of expertise we would like, I mean, the kind of features we would like to have in our cognitive architectures. We don't have the tools. I mean, when I say we, I mean, let's say people interested in building the cognitive architecture may not have the tools to build it. While people who have the tools to build it may not have as their main interest that of building a cognitive architecture. So I think both groups have to sort of release some of their constraints and see if we can go ahead. But I also agree with you that we may not have the right tools to implement it. But as we don't have others besides the quantum stuff, I think we need to try to do that using what we have.
Yeah, again, of course, you're right. You're right. In fact, the only proposal that we can have is let's consider the current state of software development as it is. So the current state of development. So something that could be replaced by something else.
Yes, let's try that as long as, I mean, and then struggle as you are doing, to find something different to see if it is better than what we have now. Yeah, the other stream is neuromorphic computing, that's the other important stream, but even there, still very hard to use, but it's another promising path.
I have a question, Fulvio. Thank you for this talk and grounding it in the history of AI and connecting, presenting all those different architectures. My question is perhaps another assumptions. I mean, when you come up with a new architectures, you try to exploit its potential to the maximum and oppose it to other architectures, while maybe in reality you need all those architectures depending on, and there isn't one architecture that can solve everything that is needed to make an intelligent system. And I would like to have your comments on Society of Mind, which is kind of a frustrating book because it doesn't present an unified version. It just presents so many different elements, and each one of those elements is a research program, full research programs. But I think it's done by somebody who has a very strong intuition on the field, and I would like your comments on those ideas.
Yeah, so indeed, when also thank you for these questions, which is both historical but well centered in the current debate. So I have to admit that when Giulio was asking that question before, the Society of Mind came to my mind, in the sense that one of the replies was that, okay, but with the current view, aren't we building in software engineering terms bad surrogates of a society of mind that was theorized? It was 79, I think, if I'm not mistaken. Now I can't remember. I can't remember. I remember that there was this idea that I was really stuck when I read the Society of Mind. It was the one related to the K lines. The K lines related to the traces of memories, whatever. And to be honest, the idea of the K lines, it's something, I mean, from that point I started to say, but maybe the big deal is in the connection, is not in the single societies. Okay, because indeed the Society of Mind, you have a number of agents, whatever, I mean, a number of societies, hierarchically organized, and then they do things. They chat, they push, they say a lot of things, and then you have that one action, one single word or whatever comes out, no? But you have all of these parallel things going on. So in my view, we, I mean, sorry, based on that, another thing that came to my mind is obviously the work by Daniel Dennett, for instance. Consciousness explained is one prototypical examples, although it has been elaborated. But the idea, for instance, of Joycean machine, there's something that is rewritten constantly, no? And you have all these things and truth values, or fragments of knowledge that are replaced and combined. So that, that's another thing. So probably we may be able to design with current software engineering terms, of course, a society of mind, like CCC system, no? The multi-agent architectures, all of them are scheduled in parallel, all of them generates data, and we have some nice mechanism to put everything together, no? That is possible, and indeed, the exchanging of messages is the big deal, no? So how we put everything together. Well, in my opinion, in doing so, the question could be: is that a sufficient level of description for cognition? Again, is the same thing, no? Because of course, for instance, in Daniel Dennett's book, in Consciousness Explained, he says, I define conscious everything that is organized in a certain way, which is okay. But that is very scientific in the sense that this is organized in a certain way given our current knowledge. So my point could be, let's define what is the meaning that we give to cognition given the current level of the engineering knowledge to build it. But if we have better tools, we shouldn't be constrained by that level of description. So in my opinion, again, I think we can actually replicate probably what is written in the Society of Mind, or replicating a model based on Joycean machines. The only model that we can replicate are the Roger Penrose's assumptions about the microtubules, assuming quantum effects for explaining consciousness. So nothing to do with quantum computing, of course. So all of these models are based on current, in my opinion, state-of-the-art computational models, are von Neumann in their essence. There is no, according to my understanding, no one of those models cannot be implemented in a von Neumann machine. So they can. So we could, and that's definitely possible. Only the bit of information is, let's consider that that's not the ultimate grammar for building those kind of architectures. Maybe there is something hidden below.
Thank you. There will be so much to discuss. So
too much. But that definitely good.
Yeah, thank you. So in light of this last discussion, my earlier questions that were going to be super in-depth about some of the studies really feel trivial. So I think it was a very nice note to this last discussion to end. I would maybe like give a random remark, which is I was very pleased to hear about the quantum robot project, because very recently I came across a paper on quantum decision theory from I think it's not 20 years ago, but it's early 2000s from Yukalov and Cernet, which is kind of designed in human decision theory. So it's still away from robot cognition, but it's about dealing with the uncertainty in decision making, and more specifically with irrationality. So in observing decision making in scenarios where there should be some rational behavior based on the risk, on the reward, still analyzing the data from people that did not behave as predicted. And this is the model envisioned to deal with that. So I know that there is a group recently at KTH that are trying to slowly do this in also in perception a bit, also in cognitive decision making, and it's something I really want to explore in the cognitive robotics field. So it's nice to hear that quantum computing is being brought in robotics.
Well, ironically, I have to say that in my opinion, currently the major barrier for the introduction of this kind of techniques, beside knowing a bit of quantum computing, the quantum theory, so there is a barrier for doing that. But the major one is on software engineering. In the sense that currently there are tools. So if you look at tools from IBM that we were using, the first thing that we did was to build a middleware wrapping all the strange things that you have to write down, and obtain something which is very software in software engineering terms, very user friendly. No, but again, so it's like writing in Python, mostly, now. But the point is that I'm kindly asking myself, maybe doing that, we are simply over constraining what are our possibilities, because now we have a model that is conceptually speaking not different from a scripting language, and again, maybe we have been trapped again in the old software engineering comes first, and then we build something. No, so it's a better of understanding the trade-off between the tool that you're using and the thing that you're doing with the tool. That, in my opinion, is still something to be managed. So, but they're starting to they start to do something related to quantum computing in robotics, specifically for the algorithms, because there are specific algorithms that can have benefits. Of course, the majority of the things are simulated, right? I mean, having access to a quantum computer is not difficult. So the IBM framework is open. I mean, you can. It's the APIs are free for everybody. But like in the old mainframes, there is a very long line to access to them. So you have to submit your code, and maybe after a couple of months, you get a reply. You get an email back with the various results. So again, also in that case, it's a bit going back to
not good for real time. Huh?
Not good for real time.
Doesn't sound like it, no.
Nice path to go through. Yeah. Okay. Well, I mean, I think we can free Fulvio, and thanks Fulvio very much for the talk and for the interesting discussions at the end. Certainly, it was very nice. It had a very nice contribution to the overall idea of iCog.
Yeah. And so, thank you for your patience and for having me.
No. Thank you very much.
Thank you very much, Fulvio.
Thanks a lot.
Okay,
good. To the attendees.
Okay, so
take care and have a nice weekend.
Have a nice weekend too. Bye bye to everybody.
Ciao.
Bye bye.
Ciao. Ciao.
Bye. Ciao.
Ciao.